But in transverse momentum space, this band edge diagram would move up at a certain pace in K, and so would this resonance. And if these bands move up at different paces for different voltages, you start to detune this resonance. So the emitter resonance would be at a different energy than the central resonance. So for different momenta, these resonances don't align for the same voltage. Here's another way of looking at that. That's tracing the well subband and the notch. So the well is the central RTD and the notch is the emitter bound state. And they move up in momentum space differently for different voltages. In our normal thinking is we say, okay, we pull this resonance past the emitter state and we always forgot about the transverse momentum. But what you do is you pull two buckets with parabolic or quasi-parabolic dispersions past each other. And they don't perfectly overlap. So you have perfect resonance for different Ks at different biases. That means this perfect resonance in a parabolic assumption is just not quite right. The perfect resonance doesn't exist for one bias point for all K points. It's spread over bias and K. And if that's the case here, then you get very nice agreement with experiment and theory. So a 1D integration, even in full band, will overshoot the current flow dramatically. And you can see that also, again, on the log scale. So if you just do a 1D integration, and you can also find that in the tool that's on the NanoHub with effective mass, you can drive it into conditions where you suddenly see a funky spike on top of the RTD. That is because you assume that you have two buckets of parabolic dispersions pulling them past each other, and for one bias, they're all perfectly aligned. That gives you a tremendous current. And you need certain potential configurations to really generate that, which happen to be typical in indium gallium arsenide devices. So, and that is true in a couple of experimental data sets that I'm showing you here in this graph. So doing a 2D integration really fixes these unphysical results, these unphysical spikes. Then the last item that you have to do well is something we touched base on in the previous lectures as well. If you have asymmetric structures, you have significant potential charge accumulation or charge depletion, and therefore the peak voltages move to smaller voltages or higher voltages. Okay? So your peak will be at different positions in voltage depending on the degree of charge accumulation or depletion. So if you do that all together, you can sort of see here in a negative bias, the peak is at a low bias point if you have an asymmetric device, or if you have a high voltage, you can sort of see the other bias direction, it moves to a higher voltage, and you can argue again that you have different potential drops. One has charge accumulation on the right, and the other has charge depletion on the left. So in one case, the potential drops over the whole RTD, in the other case, it only drops in the collector. And therefore, the potential landscape is different, therefore the IV characteristic is different. And if you put this all together, full band integration, multiple bands, charge self-consistency, boundary conditions, and you spend enough compute time, you can overlap experiment in a whole sequence of devices. So here again are our results from a structure where we varied systematically one barrier and made it more and more asymmetric, and you can see how we follow the current flow very nicely in overlap experiment. Then there's another effect that we haven't talked at all about, is the following. Let me just highlight this briefly. If you sweep the voltage in one direction, you get one result. If you sweep the voltage in the other bias direction, you might get a slightly different result. Here, in this negative differential resistance region. That has to do with charge accumulation or depletion in the well. In one case, when you come from low voltages, the resonance is full, and you need a higher bias to pull the resonance down. If you come from the other bias direction, the resonance is empty. So it sort of floats under the supply function, and eventually it pops up and gets filled at a different voltage. Now, that is exacerbated by the fact when you assume that all transmission for all Ks happen exactly at the same K and the same voltage. But if you have a distributed way of aligning all these resonances over voltage, you start to fill them at different biases for different Ks, which means you roughly eliminate this bistability. So what some people pursue as something intrinsic to a device, this bistability, there's a bunch of publications on this in effective mass models, is just really a shortcoming of your model. Has nothing to do with physics. Another effect that reduces bistability is scattering. If you're moving forward in one bias direction, you get slightly different results than going in the other bias direction. That again has to do with this picture of filling states. And if you have a way to fill lower lying states, that means you fill them, they pop up into a sea of electrons, and they're not depleted with charge. So again, you can reduce that bistability, and it turns out that it's really just a numerical artifact or model artifact in terms of central RTD in a symmetric device. Of course, you can construct a asymmetric device that has charge accumulation and depletion, and then you will have bistability. All right. So, in summary here, we have another example of having a systematic spacer variation in length, and we follow the experiment nicely. We have a well variation, and we follow the experiment nicely. And we had a spacer variation, and really what it meant is putting in more physics, matches experiments, and reduces sort of the artificial bistability that was being seen in numerical results. And that gets me to the conclusion of this segment, where I like to sort of state my personal opinion of where the state of the art in 1998 was. That scattering inside the RTD is only important at low temperatures. It's not important for room temperature high performance devices. Scattering inside the extended contacts is of utmost criticality to properly model the filling of these notch states and their broadening and the injection of carriers into the central device. Charge self-consistency everywhere in this device, not just in the Mickey Mouse central region, but in the big device, is critical. And that Bandstructure, an atomistic device simulation, was the critical understanding for high temperature, high performance devices. You need to include the non-parabolicity, the band warping. You need to keep the integration over the full Brion zone, not a simple 1D integral. And if you put that together, even without scattering in the central RTD, you can pretty much explain all of the high-performance devices that are out there. You can still construct devices where the valley current is going to be having a strong influence by scattering. But those are typically not devices of experimental, of high-performance interest. They are specialty devices where you can peel out the effect of scattering, like at cold temperatures. But high current density devices are not dominated by scattering. The other punchline here is that NEGEV is really the baseline of an industrial strength simulator, and it was available to universities and experimentalists. Unfortunately, it's not quite available now. That's a sort of a sad story.